This is lecture 32 of Condensed Matter Physics 1. And we are going to start today looking at electrons in a solid again, but more rigorously. So, what we are actually developing now is band theory. And this will explain some properties of metals and will be crucial to understanding semiconductors and insulators. Of course, we are talking about electronic properties. So, to begin with, let me recall the free electron model of metals or conductors, where I had the Hamiltonian as minus h cross square over 2m del square. Let me, in the context of this lecture, call this h 0, and the wave functions were specified by k, which was 1 over square root of v for normalization. V is the volume over which periodic boundary conditions are applied, e raised to I k dot r. And here momentum was or is a good quantum number in that it is conserved, and momentum of each electron is given by h cross k by h cross k. That is it. Now, what we are going to do, this explained many things, but one thing that was not explained, and I will just mention that, was the positive Hall coefficient for materials like beryllium, aluminum and indium. I would like you to go back to that lecture and see that these are positive. In fact, as we develop the theory, you will also see why Be and Mg are conducting. So, to understand that, we have to come up with band theory, to which the free electron theory is an approximation, but a good one for many materials of that. So, what we are going to do is perturb the free electrons by a weak periodic potential. Now, a couple of comments here. One, this is valid for metals where ionic potential is screened by electrons. That is number one. Number two, I also do it because treatment is easy to work out. But the results are general. So, once we develop this understanding, you will see that going to the rigorous theory becomes quite easy. So, what we are doing is taking V r, which is periodic in a crystal. That means V r is equal to V r plus r. R is that primitive or the smallest distance over which the periodicity takes place, and taking it to be weak and see its effect on energies of the system. And this is known as nearly free electron model. This is nearly free because they are free, but perturbed slightly by this periodic potential, and as I said earlier, valid for conductors, and then its results are general enough, and this will lead to something called Bloch's theorem for periodic potentials. That will be the rigorous treatment. So, I said earlier that the Hamiltonian now will be H 0 plus this V r, where H 0 is equal to minus h cross square over 2 m del square. The wave functions psi 0 are of the form 1 over square root V e raised to I k dot r. The eigenvalues epsilon k 0 unperturbed is going to be h cross square k square over 2 m. This we have done in the past. The new thing is that now I have a potential V r, which is periodic, and therefore, this can be expanded in terms of reciprocal space vectors. So, I can write this as summation n V n e raised to I g dot r n g dot r, where g is the smallest reciprocal vector, or I can also write this as summation over g n. I am just to emphasize that I am actually adding over all these reciprocal vectors. I am just changing the label here, just to make you understand what we are doing. So, this is like a Fourier transform, and we have done this in the past for density of electrons while considering the X-ray diffraction. So, this is a new thing, and I am going to treat this as a perturbation. So, V r, which is written as summation V n g e raised to I n g r and g. I am using a slightly different notation from the book, because I want to say that g is the smallest one. Then before I proceed further, I would like you to show something. I would like you to show that V minus n g is equal to V g star. Show this. Well, this should be n. Now, let us do perturbation theory. And let me remind you here what you did. Theory up to second order from your quantum mechanics course, and I think for you it's covered in physics 432, and also recall degenerate. Perturbation theory. So you need to go back and brush it up a bit. I'm just going to take those results directly. So the change in the energy E first order is going to be given as expectation value. This is for the kth wave function, psi k v g psi k. I am applying periodic boundary conditions over volume V. So, this can be written as 1 over V integration of e raised to minus I k dot r summation, now this is V r, sorry, V n g summed over n e raised to I n g r e raised to I k dot r dr. So, this is nothing but 1 over V, this V is the volume, summation e raised to minus I k dot r and k dot r cancel, they give you 1, summation V n g e raised to I n g dot r dr, and this is over this box of volume V, and this is V 0, which is a constant. So, all that the first order is doing is shifting the energy, which was minus h cross square k square over 2 m by a constant V 0 independent of k. So, this is actually a trivial term. And we can take V 0 to be 0 without really affecting anything. After all, potential is defined up to a constant. So, first order really does not make any difference. So, we can conclude that first order change and energy is trivial and can be taken to be 0. Now, we come to second order. Again, recall that the second order change delta E 2 is going to be summation n g, g is the smallest one. So, I am just writing that n there, V psi k psi k plus n g over E k minus E k plus n g. I am writing this by skipping a step, and this step that I have skipped is here. The second order perturbation energy is actually given as summation all the other states k prime, this is for kth state, not equal to k, k prime v k over epsilon k minus epsilon k prime. And what I am claiming now that k prime is going to be only that k plus ng. So claim is that k prime is equal to k plus ng. Only k, or if you add ng to k, only those contribute to the second order energy. Let me show that. So you're calculating k prime v k, which is equal to integration 1 over the volume e raised to minus k prime dot r summation ng, and not equal to 0 because we have taken that 0 term to be 0 anyway, v ng e raised to I ng dot r e raised to I k dot r dr. And this is going to be delta of k prime comma k plus ng v ng summed over k prime. So this is non-zero, or this is only k prime, so I don't have to sum it over. Summed over ng. So you see that k prime equals k plus ng, and therefore this relationship, the blue one. So you get summation ng psi k plus ng v psi k over this. And this you have seen that is v and g, and therefore I can write delta E 2 is equal to summation ng v ng mod square. Let me see if I wrote a mod square there, or I had not written a mod square. Correct that, please. Divided by E k minus E k plus ng. This is for kth state. Note, I had not taken v k k plus g mod square in the previous slide. Please correct it. Now let me make an approximation to understand things, and that is based on this. See, Ek is equal to h cross square k square over 2m, and Ek plus g is h cross square k plus g whole square over 2m. So as I increase n, that difference becomes larger and larger. Let me look at the smallest term. So look at the smallest Ek minus Ek g. So n equals 1, and write delta E2 for the kth state as mod Vg square over Ek minus Ek plus g. G, let me remind you, is the smallest reciprocal space vector, and Vg is that gth component. So this is fine. What I can do is, let me just focus on positive k. I can take the energy, which was the unperturbed energy, h cross square k square over 2m, and add the second order energy to this, and I'm adding second order energy to this. So there will be some slight modification. something is happening until I hit k equals g by 2. And there is a problem. Why? Let's check that. So, what I am doing is I am plotting this energy versus k. This is free electron. Then applying perturbation theory. So, it changes a bit, and near k equals g by 2, I am saying this is problem. What is the problem? Let us look at k, epsilon of k equals g by 2, which is equal to h cross square g square over 2m. And if I look at epsilon k, let me put it minus g, okay, which is equal to h cross square g square over 2m again. So, this is energy levels are degenerate. So, I am looking at k greater than mod k, actually mixing 1 and 3 dimensions. I will just talk about it in the positive side, whatever that means. And V g mod square is same as V minus g mod square, and therefore, at E k equals g by 2, if I mix E k minus g by 2, the change in the energy, second order change in the energy for kth level is going to be V g square over E k minus g by 2, and this is a problem, because epsilon k equals epsilon k minus g by 2. So, I need to apply degenerate perturbation theory here. Let me now show this in 1D, that is easier to understand. So, let us switch over. It is easier to understand, but results are again general. So, what I am doing is I am taking this lattice with distance a, so that g is 2 pi by a, and the energy E k, now no vectors, is h cross square k square over 2m. First order change will be 0. V potential V x is periodic, so this can be written as summation n V n e raised to I 2 pi by a n x. The 2 pi by a is g, and the second order change in the energy of k is going to be V 2 pi by a over epsilon k minus epsilon k plus 2 pi by a, or so I am going this way. So, energy out here becomes minus, so it is actually E 2 k equals V 2 pi by a mod square, I am forgetting that, divided by E k minus E k minus 2 pi by a. Again, this is fine, yeah. So, what I am doing is, let me remind you once more, the second order energy is given as summation n V n g mod square over epsilon k minus epsilon k plus n g by 2. So, when I take only the first term V n g by E k minus E k plus n g by 2, this blows up when k equals or E k equals E k plus n g by 2. And in the present case, it will blow up when k equals k minus 2 pi by a. And therefore, I need to apply second order degenerate perturbation theory. So, second order is blowing up here. And what are mixing here? Epsilon k and epsilon k minus 2 pi by a. And this is k equals pi by a. Let us apply degenerate perturbation theory. What do you do in degenerate perturbation theory? You take h k k, h k minus 2 pi by a, k minus 2 pi by a, v 2 pi by a, v minus 2 pi by a, write minus e, take the determinant and make it 0. And you solve it, what you are going to get is E equals, since epsilon k or k minus 2 pi by a is the same, epsilon pi by a plus minus v 2 pi by a mod. Only taking one term in that perturbation that was blowing up. So, what is happening is that this energy, which was continuous with respect to k, at k equals pi by a, it suddenly gets two different values. One value is here and one value is here. So, this thing splits. There are no energies in between. So, I am going to erase this, and what you get instead is something like this out here and then the energy out here. There is a gap, no energies here, no eigenenergies. Energies are only up to this. So, what was a continuous distribution has broken. Let me now do it a little more rigorously. So, one thing you notice is that this is opening up at the zone boundary. Similarly, if you go to the other side, now let me extend it to the negative side. If I go to the other side at k equals minus pi by a, if I take that second order correction V n g mod square over epsilon k minus epsilon k plus n g at k equals minus pi by a, E k plus 2 pi by a is same as E k. So, again do degenerate perturbation theory. And then you do that and you get exactly the same thing. There will be a split. So, what I have argued now is that if you first order change in the energy vanishes, even with this very weak potential, the two different plane waves start mixing up at the zone boundary, and that opens up a gap and breaks the continuous energy spectrum into two different levels. Let me develop it a little further. So, if I were to calculate energy up to this point, k equals pi by a. Let me focus on, since I am doing in 1D, k greater than 0. So, if I were to calculate E k for k between 0 and pi by a, what you see is that if k is not equal to pi by a, I get energy equals epsilon k plus summation V n g over E k minus E k plus n g, this is mod square, summed over n. So, this I can do, and the only keeping n equals 1 may be okay, because E k minus E k plus g will be much smaller than E k minus E k plus 2 g and 3 g and so on. So, we try to understand keeping one term is fine, except that when you go to k equals pi by a, then you apply degenerate perturbation theory. So, we seem to be mixing two things. I would much rather do a single calculation. So, combine this to do a single calculation. And that will be that I will take this psi k to be already a mixture of e raised to I k dot r, in this case 1 d, so I k x, plus this is also not a vector, c k minus 2 pi by a e raised to I k minus 2 pi by a x. So, I am mixing only two plane waves. And diagonalize the Hamiltonian with these to get E. Okay, so, I am taking a space which is spanned by e raised to I k x and e raised to I k minus 2 pi by a x, and calculating the expectation value of Hamiltonian with respect to these two, and see what the wave function looks like, what the energies are. So, for k greater than 0, that is k between 0 and pi by a, I am taking psi k equals c k e raised to I k x plus c k minus 2 pi by a e raised to I k minus 2 pi by a x. This automatically mixes those two wave functions that I am supposed to mix, but calculates the energy for all other k's also by mixing these two. So, I am mixing only these two wave functions and calculating the expectation value of h. And if you do that, what you will find this, and I will leave this as an exercise for you, as mod c k square epsilon k plus mod c k minus 2 pi by a square epsilon k minus 2 pi by a plus c k star c k minus 2 pi by a v 2 pi by a plus c k minus 2 pi by a star c k v minus 2 pi by a. That is the expectation value of the Hamiltonian. You can check that this is real. And what I will do is I will minimize this with respect to c k star, minimize this with respect to c k minus 2 pi by a star to find the values of c k's, with the condition that psi be equal to 1. Okay, so, this is minimization with a condition. recall technique of Lagrange multipliers from classical mechanics. And that's what we are going to do. We will take the Lagrange multiplier to be E, that's what it comes out to be, the energy, and do d by d Ck star of H minus E psi psi minus 1 equals 0. I'm just giving you the steps. D by d C k minus 2 pi by A star H minus E psi psi minus 1 to be equal to 0. This gives you the equations for Ck and Ck minus 2 pi by A, and this gives, let me write the equations. You will have to work out these things. This gives you epsilon k minus E Ck plus V 2 pi by A C k minus 2 pi by A equals 0, and V minus 2 pi by A C k plus epsilon k minus 2 pi by A minus E C k minus 2 pi by A equals 0. These are the two equations for the coefficients, and if the coefficients have to be non-zero, two sets of linear equations. So, if Ck is non-zero, Ck minus 2 pi by A is non-zero, then you should have determinant of epsilon k minus E, V 2 pi by A, V minus 2 pi by A, epsilon k minus 2 pi by A minus E, determinant equals 0. And that gives you the energy eigenvalue. What does it give you? It gives you epsilon k minus E, epsilon k minus 2 pi by A minus E, minus V 2 pi by A mod square equals 0. You work out the energies. This is a quadratic equation, and you get E equals epsilon k plus epsilon k minus 2 pi by A plus minus square root of epsilon k minus epsilon k minus 2 pi by A whole square plus 4 mod V 2 pi by A whole square divided by 2. So, what you have done is, by mixing those two plane waves that you are supposed to do for doing degenerate perturbation theory, you have actually calculated the entire k dependent energy for k greater than 0. If you plot it, you will get two eigenvalues, because I am mixing after all two different energies. You are going to get a curve something like this. Up to this point, and upper one comes out to be like this. There is a cusp here. So, here there is a split. Notice I have stopped at k equals pi by A. I will comment on what happens beyond that in a minute. Now, you can do exactly the same thing on the other side. What will happen on the other side is, you will get, instead of k, k plus 2 pi by A. Let me just do it explicitly. So, what we found is that E is equal to epsilon k plus epsilon k minus 2 pi by A plus minus square root of epsilon k minus 2 pi by A whole square plus 4 V 2 pi by A mod square divided by 2 for k greater than 0. For k less than 0, that is k between minus pi by a and 0, you will find E equals epsilon k plus epsilon k plus 2 pi by a, because this is the term that blows up in that second order expansion. So, I mix these two, square root of epsilon k minus epsilon k plus 2 pi by a whole square plus 4. V remains the same because V minus 2 pi by a and plus 2 pi by a mod square are the same, divided by 2. So, on the other side also you get the same thing. So, what I like you to do is plot these two energies in their respective regions using a computer, and what you will find is that this is the plot I get. I will plot it only up to pi by a minus pi by a, and for each k I am getting two different energies. So, lower energy looks like this, and if you have done a proper plotting, you will get the upper energy to be like this. So, what should have been a continuous curve has broken into two bands. These are called bands. So, this is band 2, band 1 of energies. I will comment in a minute about this, what happens here, why there is a cusp, and what happens when you go beyond pi by a. But this is what I want you to plot and get at. Just to recap, we took the 0th order Hamiltonian to be minus h cross square over 2m d2 by dx square, V potential to be a periodic potential V n 2 pi by a e raised to I n 2 pi by a x. We have taken V 0 to be 0. Applied perturbation theory, then E 1 with this 0 came out to be 0. E 2 came out to be summation over n V n g or n 2 pi by a mod square divided by epsilon k minus epsilon k plus n 2 pi by a. N varies in both directions, and then we found that for positive k, k minus 2 pi by a was degenerate at the Brillouin zone, and therefore applied degenerate perturbation theory. And instead of doing that, we mix these two energy levels right from the beginning. So, if I for k greater than 0, we took psi k to be some c k e raised to I k x plus c k minus 2 pi by a e raised to I k minus 2 pi by a x, diagonalize the Hamiltonian, and then we got that band, two bands of energies. Now, next question I want to ask is, what happens for k greater than pi by a? So, I am just focusing on one side, and you may have realized by now, if you go to the other side, it is just a mirror reflection of that. So, let us see now what I plotted up to pi by a was by mixing a k here, let us say this is k, and I mixed it. Let me make the origin slightly to the left, because I want the other side also. This is my k equals 0, this is my minus pi by a, and I mixed it, this k value with k minus 2 pi by a. So, I mixed it with something out here. This is k minus 2 pi by a. Now, I want to go beyond pi by a and look at a value here. The corresponding k minus pi by a will be here. So, let us write this k, let me make this k minus 2 pi by a. By symmetry, now for this k, the red k, this energy E k minus 2 pi by a is exactly the same as this E k, green one, because I am taking the same distances on both sides. And this energy out here is the same as this energy. So, let me write this in with color code. I am going to say that E k, k greater than pi by a, is same as E k minus 2 pi by a, where this red k is slightly greater, and E k minus 2 pi by a is same as E k by symmetry. And anyway, V 2 pi by a square is the same. So, if you go back to the energy expression, they will come out to be the same. So, let me say it again. I am plotting the energy curve. This is pi by a, this is minus pi by a, and I am taking a k out here, which is a distance from the Brillouin zone, and I go exactly the same distance with the Brillouin zone on the right side, and I want to know what the energy out here is, if I apply whatever I did just now. Corresponding to this, the k out here was this, and corresponding to the right one, the k out here is this. This energy is the same as this one. Let me just encircle them. This energy is the same as this one. This energy is the same. This energy is the same as this one, and this energy is the same as this one. So, if you write in the expression E, which was E k plus E k minus 2 pi by a plus minus all that divided by 2, the energies for beyond Brillouin zone and before Brillouin zone are the same. So, if you were to plot it, you get energy level like this, and again it will go like this. You will get a very good feel for this again if you go to the computer and plot it. This is for k greater than 0, and this is for k less than 0, and as I said earlier, on the two sides you mix the k's appropriately. I am right now, whatever argument I have given are for the right side, exactly the same arguments are given for the left side. So, this is what the energy is going to be. Showing it again, I am getting energy like this. This is the Brillouin zone, and then starts like this. For the upper band, you will get an energy like this, and then it repeats until you hit the next point, which is the second Brillouin zone. There will be E of 2 pi by a will be same as E of 2 pi by a minus 4 pi by a. So, I can say that E g will be same as E g minus 2 g. So, you will have to apply perturbation theory again and mix those two levels, and that makes this smooth out here. It will not affect the energies for the lower band that much, but it will affect the energy of the upper band. So, in general, what you should be doing therefore is, if I write up psi k, taking care of all those points where degenerate perturbation theory comes, you should be writing this as summation over all NGs e raised to I k dot r sum Ck plus C k plus g e raised to I k plus g dot r plus all higher order g's, all higher order g's. And this gives Bloch's theorem, which I will talk about a little later, but right now that is what it is. So, what I would like you to do is plot the lower band of energies by taking mixture of epsilon e raised to I kx and e raised to I k minus 2 pi by a x for k less than 0 and e raised to I kx and e raised to I k plus 2 pi by a x for k, this is k greater than 0, k less than 0. Only the lower band, and what you will get is something like this. And this is what is called a band. And I have already told you that in this, if you mix only two of these, upper band is going to come with this kink. But that kink gets removed if you take care of mixing properly at k equals 2 pi by a. That also I will make you do. But right now, the lower band is more accurate, and this is what you want to get. So, conclusion is that by mixing these plane waves, you get these bands of energies. The continuous curve that was there for free electrons gets broken into bands. So, these are the band of energies with a band gap. And this band gap occurs at pi by a, minus pi by a, 0. And if you mix more, I am just anticipating the results, you are going to get something, a higher band like this. So, here also there is a band gap, right. So, this occurs at band gap occurs at G, 0G, 1G, 2G, or if you take the Brillouin zone, you shift the whole thing. So, at Brillouin zone boundaries. So, this is what we have learned, and this, the wave function psi, is a mixture of all g's, k plus g. So, let me write n g, c, n, e raised to I, k plus n g, x. And this is what gives rise to Bloch's theorem. But before getting into that, let me recap. 1, and I will just focus on the lower band. Energies in a periodic potential given by solving the Schrodinger equation such that in a band, and we have already understood that there is a band that develops, E of k equals E k plus G. So, what we are talking about is that you develop this band and you get energies like this. And this is pi by A minus pi by A. This is very much like phonons, where we had omega k equals omega k plus G for acoustic as well as optical branch. And just note, this arises due to periodicity of V. For phonons also V was periodic, for here also V is periodic, there we took it to be quadratic. Number 2, as a result of 1, we can specify state of an electron by k within the first Brillouin zone, again exactly like phonons. And because we are doing within each within the Brillouin zone and a band index. You saw already, if I mix 2 plane waves, I get 2 bands. If I mix more, I'll get more bands. In phonons, I was getting acoustic and optical bands, if you like. Here I get electronic bands, so I can just restrict myself within the first Brillouin zone, because after all it's repeating after that. That's number 2. Number 3, because of periodicity of V, there is a gap at zone boundaries or at k equals 0. Okay, so you get these bands and gaps in between. So this is what we have learned so far through all this. This is the take home lesson, that because of this periodic potential, different plane waves start mixing, and when they start mixing, the energies break into bands, and when they break into bands, there are gaps in between, right. So let me just summarize this with a picture, that I'll just focus within the first Brillouin zone. You have one band, second band, third band, and so on. So this is this whole thing is band 1, this whole thing is band 2, this whole thing is band 3, and they have arisen out of that free electron diagram, which would have done this. And because of this periodic nature, I can fold everything back into within the first Brillouin zone. If I do that, just for some completeness, I'll show you the free electron picture also here. If I do that, I would have gotten this, then this, continuous bands, and they have now, instead of continuous, you have gotten these bands, and here are these band gaps. And this is all due to the periodicity of the potential, very systematic and pattern wise. Let us now count the number of states in each band. Recall, how do we apply boundary conditions here? This is again using boundary conditions, periodic over L or n cells, exactly like phonons or exactly like free electrons. So, I have the wave function, just looking at that wave function, which is a mixture of I k minus 2 pi by a x. If I apply the boundary condition over L or over n cells, I am going to have this as c k e raised to I k x e raised to I k n a plus c k, this is k minus 2 pi by a, minus 2 pi by a e raised to I k minus 2 pi by a x times e raised to I k minus 2 pi by a n a. This is going to be the new wave function, and I want this to be exactly equal to psi k. Now, look at different terms. This 2 pi by a n a e raised to I, this whole thing is 1. So, that part I am not really bothered about. What you have is that e raised to I k n a here, and in the first term this should be 1 if you apply the periodic boundary conditions. So, if you apply the periodic boundary conditions, that is, demand that psi k x plus n a be equal to psi k x, this immediately implies e raised to I k n a is equal to 1, and therefore, k equals 2 pi by n a times n is equal to 0 plus minus 1 plus minus 2, and for within the Brillouin zone, what you can write is k equals 2 pi by n a n between minus n by 2 to n minus 1 by 2. And if you count these, this is exactly n k values. Again, go back to free electron theory, go back to phonons, and there also we saw that there were n k values within the first Brillouin zone. So, in this band, there are exactly n k values. I will take the last one to be on the Brillouin zone here, and on this side I will not count that, because this state is exactly equivalent to this by mixing, right. So, k equals pi by a is equivalent to k equals minus pi by a. So, I do not want to count it twice. and these are n values. For n tending to infinity, these are discrete, but k goes to very delta k goes to very small values, right. 2 pi by n goes to 0, but discrete still. So, these are known as again quasi continuous case, and there is exactly 1 k in 2 pi by L. So, the density again is L over 2 pi. So, all the mathematics remains the same as was done for phonons or for free electrons. Right. So, what we will do, all this we will consolidate into Bloch's theorem in the next lecture. In this lecture, I just want to now conclude what we have done. Number 1, in a periodic potential, the potential mixes plane waves e raised to I k dot r and e raised to I k plus n g dot r, n equals plus minus 1 plus minus 2 and so on. Number 2, this divides the energy epsilon k equals h cross square k square over 2 m into energy bands with gap at k equals 0 and zone boundaries. Third, E k versus k is periodic. So, all electronic states can be specified by k within the first Brillouin zone, and fourth, number of electronic states in each band is n, where it is understood that we are applying the periodic boundary conditions over n cells. This is conclusion drawn from whatever little perturbation theory and mixing we did, but it is enough to teach you what all you can do. So, I would really urge you to do numerically the problems that I have given you, plot them, and that will give you a very good feel for the bands and energies in periodic potential. And what we will do is consolidate all this into Bloch's theorem in the next lecture. Thank you.